Okay, so welcome everybody. It's a pleasure to have Paolo da Vela today. Paolo got his master in Florence, then he moved for a PhD in Siena and Pisa. He was telling me 2 minutes ago. And then he moved for a short amount of time in Bari, if I remember correctly. Then 4 years in Innsbruck, and then since 2023, he's here at INAF as a researcher. And today he will tell us about probing the cosmic magnetism with gamma ray observation of extragalactic sources. So please, and I will tell you while 5 minutes before the end.
It's 25, right?
Yeah.
Okay. So here they hear me, right? You check the.
Yeah.
Okay, perfect. Okay, so. As already I was introduced already, so today the topic is a bit peculiar. Probably I will try to be as much clear as possible because I understand that it's a very peculiar topic. So I will talk about the possibility, basically how we can prove the cosmic magnetism using extragalactic observation of gamma ray observation of extragalactic sources. So I first introduced basically the principles, the context of the talk, and then I will move to the technique with which we can measure the magnetic field in the intergalactic medium, and then I will present the latest results. So, okay, cannot change. Yeah, it's just up and down. Okay. So the main context, so the context of this talk is the following. So we have magnetic fields are present everywhere in the universe, from small scale to large scale, and particularly we know that magnetic fields in the galaxies can be of the order of tens of microgauss, and recently we also know that at the edge of the cluster of galaxies we have a residual magnetic field of the order of microgauss. So this magnetic field are present in all the galaxies, but the problem is that we don't know the origin of this magnetic field. Most of the explanation assume pre-existing seed fields that they are amplified in the structure. Okay, so the problem is that we don't know the origin of these seed fields. We have several explanations, but we don't have an idea of observationally what is the main mechanism of the origin. So actually, we can distinguish among the different explanations. We can distinguish basically two main scenarios. It's more complicated than this because we can have also a mixture of these two. But we can identify two main scenarios: the cosmological scenario and the astrophysical scenario. The main difference between them is that in case of cosmological scenario, you expect that the magnetic field is originated in the first phases of the evolution of the universe, and then you should expect that a residual magnetic field should be present everywhere among the voids, among the galaxies, actually. So in the case of astrophysical scenario, then the magnetic field can be originated in the structure, and then the structure can pollute the intergalactic medium with these seed fields. Okay, but in this situation, even if at the edge of the structure you can expect a residual magnetic field, if you go sufficiently far away from the structure, from the galaxies, then you do not expect to find a residual magnetic field in the voids. Okay, so the final statement from this slide is that
it's green. Oh, okay. So I don't know. Bye.
Okay. Okay, so and that's the reason is that, so the point is that to distinguish among the different scenarios, we need to measure the magnetic field in the voids, and that's the main point of this talk. We want to try to measure the magnetic fields in the intergalactic medium. Okay, if we try to understand how we can describe the intergalactic magnetic field, we can think, as a first approximation, we can characterize the intergalactic magnetic field with two main features. So the strength and the correlation length. The correlation length is basically the length within which we can consider the magnetic field as homogeneous. Okay. So, and you can also do better. You can try to basically use the standard technique with which you measure the magnetic field in astrophysics to try to say something about this intergalactic magnetic field. For example, Zeeman split, Faraday rotation, or from CMB, there is, for example, Daniela Paoletti that is working on this. But as you can see here, if you put everything in this so-called diffusion exclusion plot, in the x-axis you have the correlation length, and in the y-axis you have the strength of the magnetic field, you see that there is a huge zone of this plot that is not reachable by any standard technique. Okay, you don't even know if it's zero. Okay, because you do not have a lower bound also. So you need a sensitive technique, a more sensitive technique that can allow you to reach the weakest magnetic field. And this new technique is used in the last decade, make use of the extragalactic gamma ray observation of extragalactic sources. And this I introduced the mechanism. Okay, imagine that you have an extragalactic source that emit TV photons. Okay, so it is somewhere in the universe at a certain redshift. Okay, depending on the distance to the source, you have that these TV photons that this source is able to emit, they cannot propagate over large distances because it interacts with the EBL, with the extragalactic background light. And through gamma-gamma pair production, you have basically the pairs are formed. Okay, and this means that depending on the distance to the source, these TV photons can arrive or not. Okay, it's a stochastic process, but the more distant is the source, you have more chances that these photons are absorbed by the EBL. Not all the photons are absorbed, but you have a higher probability when the source is more distant that these TV photons don't arrive to us. Okay, so then these photons, they are absorbed by the EBL, and then you have the production of pairs. Okay, so the pairs, they can basically upscatter in turn the CMB, the cosmic microwave background, producing again a gamma ray emission, but at energy which is lower than the primary energy. So the idea is that you have a primary source in the TV domain, then the source is partially absorbed, and then you have a re-emission of GV photons in this domain. Okay, so basically this excess is another component that you need to take into account when you do spectral studies of the source. You basically, in the GV domain, you should expect the source in the TV domain, but also in the GV domain, and then in addition, this GV excess. This is roughly how you should expect that this photon is reprocessed in the GV domain. Of course, this is a cascade emission because the pairs in turn, they can produce again GV emission. This GV emission can be absorbed again, and then so on and so forth, and you have an electromagnetic cascade. Okay, so basically 10 TV photons is reprocessed in the GV domain. As you can see here, 10 TV photons is absorbed, and then you have emission in the GV domain. This cascade emission can be observed with the current facilities in the gamma ray band, which is Fermi-LAT, satellite, and CTIO, for example, the Cherenkov telescopes in general. So we know that photons are not sensitive to the magnetic fields, but yes, the pairs are sensitive to the magnetic field. So if you have a not negligible intergalactic magnetic field, these pairs travel in the intergalactic medium, and then they are deflected, and then you can have several observational signatures that you can use to indirectly measure the intergalactic magnetic field, or at least constrain it. This is the main point. Now I'm going to talk about these three different observational signatures that can be used to constrain the intergalactic magnetic field, starting from the most important one, which is the smoking gun for the existence of the intergalactic magnetic field, the presence of gamma ray halos around extragalactic sources. So first of all, we need the sources. And of course, the sources that we know that are gamma ray emitter are the blazars. Blazars are basically represent the most extreme flavor of AGN. They basically, when you observe a blazar, basically the jet of the AGN is perfectly aligned, or mostly perfectly aligned with the line of sight. And what you see is basically the jet. The jet overwhelms over any other component, the host galaxy and any other component, broadline region, and all other component of the AGN. So we know that the blazar emit from radio to gamma ray band. They are very well-known gamma ray emitters, and they are also very variable sources. Once you have a gamma ray source, then you need to understand among this class of blazar what are the most important sources that can be used for this kind of study. So here I put three possible criteria with which we can try to choose one of the sources to do this kind of studies. So first of all, we need the hard very energy spectra. When I say hard very energy spectra, this means that usually in the very energy band, energy larger than 50 GeV, most of the spectra are power law. Okay, so we need hard power law in the sense that if you have hard power law, this means that you have enough photons in the very energy band, and this guarantees you that you have enough cascade power, and then you can play the game I described you before. So then, of course, we need the hard spectrum that arrive to the highest energies. And here I wrote proper redshift. Why did I write this? Because in principle, you can also choose a source at redshift 2 or 3. But the problem of this is that when you observe a very distant source, this source can be completely absorbed in the very energy band. You are not even able to measure the very energy emission. So basically, if you think that the most distant blazars measured up to now is redshift 1, because we are opaque in the very energy band, we can try to say that 0.1 larger than 0.1, otherwise you are constraining really the local universe. But if you go, for example, 0.7, 0.8, you might be able to measure still the very energy band. This is important because otherwise you cannot quantify the cascade emission that you can have. Among these class of sources, the most important sources for this kind of game are the so-called high-frequency BLAC object. And once you have the source, you can try to play the game. So you have a source at a certain distance. This is the observer. You have the jet. Here also you have the most general situation in which the jet can be also partially misaligned. But if you think that the source is completely aligned or more also misaligned, but these calculations are done when the jet is perfectly aligned. The jet is perfectly aligned with the line of sight. Then you have the photon is emitted, is absorbed by the VL. You have production of pairs, and the pairs are sensitive to the magnetic field. And then the cascade emission can arrive within a certain within a certain angle with respect to the line of sight, with the jet, the axis of the jet, okay? And if you do the calculation, you discover that you have two regimes. One is the regime in which the pairs, the length scale of the inverse Compton scale is much, much lower than the correlation length of the magnetic field. In this case, you do not have any dependence on the correlation length. But still, in both situations, also the opposite situation, you have also dependence on the correlation length. But still, in both situations, you see that two things. First, that the angular distribution of the photons depends on the intergalactic magnetic field. And second, depends also on the energy. This means that you can go in both energy band, GV domain and very energy band, TB domain, and you can try to play the same game. Like, for example, I go for the same magnetic field, I go to the higher energies, then I expect that the source is more compact. Lower energies is larger. So going to different bands, you can try to constrain different magnetic field strength. And also you have other dependencies, the redshift and optical depth. Okay, so, and this is what you expect. The source should be extended, the cascade emission is extended, and the extension depends on the intergalactic magnetic field. This is what the theory tells you. So what are the expectations? If you try to use, now there are several codes that are available, you can try to understand what you should expect in the observations. Okay, so you have your preferred source, 1ES0229 is a blazar, which is the most used source for this kind of studies. The redshift is 0.14. The correlation length for magnetic field is assumed to be 1 megaparsec in this case. And then if you assume a power law minus 0.5 from the GV domain to the very energy band, and then from energy larger than 1 GV, these are the expectations. So in the center, you have the source, and as soon as you increase the magnetic field, you see that the Halo emission is increasing. The spreading of the angular extension is increasing. Okay. Of course, this is not what you would see with the telescopes, because you need to convolve these with these images with the instrument response function with the PSF of the instrument, basically. Okay. Okay. So these are the expectations, and this is sadly the reality. Okay. So up to now, in spite of several attempts, both in the GV domain and in the very energy band, there is no detection of extended emission. And this is basically, in my opinion, is the smoking gun for the existence of the intergalactic magnetic field. As I will show you later, the methods that I will show you allow you to constrain the magnetic field, but to put some lower bounds on the intergalactic magnetic field. But the real smoking gun for the existence of magnetic field, intergalactic magnetic field, is the extended emission. In this context, we are working with, I'm working with Christina, that recently started a postdoc here within the context of MAGIC and CTA collaboration. And as you know, in the next years, CTAO will be the most important facility in the very energy band. And actually, LST, which is one of the telescopes of CTA, is already running, and for the moment, since the other telescopes are not yet available in the Canary Islands, the LST is working together with MAGIC telescopes. So instead of 2 telescopes, MAGIC is composed by 2 telescopes. The first telescope of CTAO is working together with MAGIC. And as you can see, basically not really the angular resolution, but the sensitivities, especially at 100 GeV, is improving quite some. It's not a lot, but still, this instrument represents now the most important facility in the very energy band for this kind of studies. This is the reason why we are leading a study with the source 1ES0229 to try to detect the standard emission, and in case of non-detection, to prepare the ground for CTAO. This is the main, and this is a work in progress that we are doing with Christina. So let's go to the second point, spectral features. Okay, what you will see now is always the same, the other phase of the same medal. The physical process is always the same, but I'm using different information. Okay, so spectral feature. So let's assume that we all understand that there is this extended emission, but what can we say about the SED of this cascade emission? So this is the point. When you have a source in the very energy in the gamma ray, sadly you have only a power law. It's not exciting the spectrum. But what happens? I told you before, no? When you go to energy larger than 100 GeV, this is the spectrum at the source. But when you try to measure the spectrum at the observer, the emission is suppressed due to the EBL absorption, and this is actually what you see. There are tons of papers that also try to estimate the EBL from this kind of absorption. Okay. Okay. So, but this basically amount of flux which is absorbed is basically what we call the cascade power that then is re-emitted in the GeV domain. And what you should expect is the following. When you consider magnetic field, zero magnetic field, you should expect also a component in the GeV domain. Okay. As soon as you increase the magnetic field, since the magnetic field is removing the pairs from your light of sight, the signal is suppressed. And then people in the last decade were playing this game, like trying to tune the magnetic field until this component does not overshoot anymore, does not overshoot anymore the data. And this allows you to say that magnetic field should be larger than, and then I have a lower bound of the intergalactic magnetic field. Okay? And this is what it was done in several papers, but the last one, which is really great papers from S and Fermilab collaboration 2023, they do a combined fit between Fermilab and Cherenkov telescope, in this particular case, the Hess telescope, and they do the fit of the spectral distribution of 1ES0229. As you can see, this is the spectrum which is absorbed by the EBL. If you deabsorb, this is a straight power law. This is a very peculiar source. So it's not always like this, but when you deabsorb the spectrum, here you have basically a straight power law. Then you absorb the spectrum, and then this is the spectrum that you have. No? And then, first of all, people verified that you don't need to add any component. Already with the power law, you can absorb power law, you can describe the data. But still, what they did, they include in the description of the model, they include also the cascade emission for several intergalactic magnetic field and several life cycle of the source, because the life cycle of the source is really an important parameter. You don't need that only that the source is emitting gamma rays, but also for how long the source emitted gamma rays, because the cascade emission that you see is delayed, right? Because the pairs are deflected and then the cascade is also delayed. So you need to know for how long the source was active in the very energy band. This is what we call life cycle. So for several life cycle and intergalactic magnetic field strength, they were able to calculate the combined fit S plus Fermilab, and they derived the best fit. The best fit. From the best fit, they use a confidence level of 95%. They also derived the lower bound on the intergalactic magnetic field, larger than 10 to the minus 16 Gauss. This magnetic field cannot be reached by any other technique. Okay, I cannot cite this other paper because in the meantime, also with MAGIC, we work on this source, and I led this publication in which we also consider not only the life cycle of the source, but also the variability of the source in the very energy band, because also the variability play an important impact. If you consider also the variability of the source in the very energy band, you have a more reliable limit, but of course is weaker, but more robust. Okay, so then we arrive to 2 times 10 to the minus 17 Gauss. Okay, this publication was done recently. I did this publication in 2023. Okay, this is what we can say about the blazars, but what can we say about transient source? Can we use the same technique also for transient source? I already told you that the signal Yeah. No, I understand. Yeah, sorry. Yes, in principle, you can play the same game, right? Because if you have a transit like a GRB, you should expect the GRB in the TV domain, a spike in the TV domain, a spike in the GV domain. But in the meantime, you should expect that together with the afterglow of the GRB, you should have also the cascade together with the afterglow. No? And if you assume that the magnetic field is large, is not zero, then you have a tail of emission, which represent the pair echo, what we call pair echo emission. Of course, what you have is that increasing the magnetic field, of course, the tail is more flat, and then the signal is more diluted in time. Okay, basically, you can play the same game. You can try to. You have the first GRB detected with magic, and as you can see, these are the magic points. Okay, the very energy spectrum, the very energy light curve. This is the Fermi light curve. What we did here, the first approach. This is the first GRB detected on magic in 2019. The time activity in this case is 40 minutes, and the redshift is 0.42. What we did is the following: we measured the flux of magic here, and then we predict the amount of cascade. But we neglect all the cascade when the afterglow is still happening. I inaugurated this new terminology. We try to measure the cascade after the end of the afterglow. It's not really clear, but basically from the end of the afterglow on. Okay, and this is what we did. GV domain, we neglect all the cascade here. We measure the TV emission, and then we try to see what happens after the end of the afterglow. For different intergalactic magnetic field, we built SED for different observation time for different intergalactic magnetic field. And as you can see, sadly, 15 days, 1 month, 3 months of observation time until 2 years, we cannot say any. Okay, but the machinery is there. Okay. And then, of course, we have to use the brightest of all time of the GRB. And this is the second work that I'm doing. We submitted recently the paper in Fermi collaboration. The results have already been presented to some conferences. And in this case, the huge luminosity of this GRB allow you to arrive to limits on the intergalactic magnetic field, which are close to the one that you can get with the blazars. This is really impressive. Okay, this is the first the GRB was observed by Fermilat and saturated the instrument and also the GRB was detected by LASO in the very energy band with a maximum energy of 13 TeV. So you have enough cascade photons. So we play the same game also in this situation, but still here, differently with respect to the other GRB, we see that the TV light curve at some point decrease with respect to the Fermi light curve. So that's the reason why we say, okay, why looking only after the end of the afterglow? Why not going into the afterglow? And then we try to model the cascade also during the afterglow. So you need to model also the afterglow in this situation, okay? So we model the cascade here, and then up to 1 year, okay? And then we did this fit in time and energy from up to 1 year. And actually you can see from the light curve, this is the light curve for different intergalactic magnetic field strength, only with the component of the pair echo, the cascade. You see that you can constrain something in this situation. If you do the things correctly, you arrive to get a limit of intergalactic magnetic field of 4 times 10 to the minus 17 Gauss. So very close to the one that you can get with blazars. But why do we play this game with GRB if we can play with blazars? The reason is that here you do not have several assumptions that you have to do with blazars. For example, you do not have to do any assumption about the life cycle because you measure the life cycle of the GRB, and the evolution of the GRB, because you measure it, you can measure. So the limits that you can get with the pair echo is more robust than the one with blazars. And then I leave you here the conclusion. So the gamma ray observation of the galactic source is a powerful tool to probe the cosmic magnetism. So of course I lie a bit because the story is nice, but there are of course some enemies like plasma instabilities. We know that the pairs, once they are produced, can undergo with plasma instabilities, and then they lose energy faster with plasma instabilities than the inverse quantum. Then you do not have a production of cascade, and then that could be really a problem for this technique. Still, the last papers go in the direction that the plasma stabilities cannot play an important role for AGN, but still, if for AGN they don't play an important role, for sure for GRBs they don't play any role because they need time to develop, to grow, and then for GRBs, since we are talking about minutes, hours, they do not have time to. So this is another advantage of taking the GRBs with respect to the blazars. And then in the future, we will have new blazars with CTIO, more GRBs, and the study that I'm trying to lead, that I'm leading, basically, I'm trying to understand also, depending on the physics of the GRB, what are the most suitable GRBs that can allow us to trace the development of the cascade during the afterglow. And this is a work that I'm doing now. That's it. I hope I didn't exceed the time.
Thank you very much. So, there is time for questions.
Sorry, I missed. What is the upper limit of the magnetic field that you got from the halos?
Actually, you don't get any upper limit with halo. You can exclude some value of magnetic field, but it's very tricky because you need to consider that when you don't see the halo, this could mean that the instrument is not sufficiently sensitive to measure the, and this you can verify it. Okay, but it can also be that the source in the past was not so active enough to give you a reasonable amount of halo that you can detect now. So you need, it's quite tricky. So if you detect it,
you get the halo, you get the magnetic field, but if you don't get, you cannot
it's tricky. It's not easy. It's not easy. You can exclude some value, but you need to work with the 2D uncertainty, let's say.
Yes. I have a question. Is the cascade univocally defined, or you can have a different kind of type of cascade, or any limitation in how the cascade can be effective apart from plasma instabilities? Whatever limitation are in
yeah, I mean, the most important uncertainty about the cascade is in how you measure the very energy spectrum, because usually what we do, you take the very energy spectrum with the Cherenkov facilities, and then you measure a spectrum up to 1 TeV. And then, but you don't know if the cascade was there also beyond 1 TeV. You assume that you can have an additional photons that you don't see because they are absorbed, and then you say, okay, you arrive to 10 TeV, and then you have a certain amount of cascade and a certain shape of cascade. But if you are limited by the knowledge of the very energy spectrum, and depending on the maximum energy and the shape of the very energy spectrum, you can have different shape and also amount of cascade. That are the most important steps that lead you to different cascade, let's say. Of course, you can have also andronic cascade. That's true. Yeah, but it's another world. Yeah, because okay.
Other questions?
Yeah. So concerning the life cycle of the process for using blazars, so we have the most common assumption regarding if are the genesis with the module
of course, yeah. So basically, let's put it this way: the safest hypothesis is that okay, I don't know what the source did before I started to observe it. Let's assume that 1S0229. That I wrote 10 years. Why did I write this? Did I write this? Because the source is observed since 10 years, monitored since 10 years in the very energy band, and then you say, I don't care what happens before 10 years. But this, of course, it's a really very, it's a two approach, because basically you are excluding all the cascade that has a delay larger than 10 years. And the source, we know that the source was there 10 years before. The other assumption that you basically do there are several papers that tell you what is the life cycle of the source in the very energy band. Usually we assume 10 to the 7, 10 to the 8 years. It's reasonable. But yeah, the safest approach is usually if you take the papers, you see 10 years. They use always 10 years. At the beginning, they use 5 years, but this is the most studied source, and for this source, we use 10 years.
And this produces the most extreme limit of me, usually.
The safest limit. Because what is the point? If you take a larger time activity, you have more cascade, and then you need a larger magnetic field to suppress it, and then you have you end up with a most constraining limit, but it's not safe. Let's say. Yeah.
Other questions? Let's see if there are questions online. I don't know. Maybe not. Maybe yes. Yes. No, that's no questions from online. Okay, so if there are no other curiosities, let's thank the speaker again. Thank you very much.
Yes.